Hello, everyone. Welcome to the new lecture on this lecture series on GANs. Today, we'll be talking about conditional GANs, which are very nice extension of the traditional GANs, and uh, these are very good in the sense that they allow us to control the output of the GANs by providing some conditional information. So let's just see like how the architecture is evolving and how you can actually make your own conditional GAN. And there are very interesting applications based on conditional GANs. So let's just see. Okay, so as I'm saying, we have a Think AI club, and many students are benefiting from our club. So if you are interested, you can join this club by scanning this QR code. Okay, these are the success stories of our students. And these are not limited to better participation in the conferences, publishing papers, going for higher studies, but also getting very good rank in the competitive exams as well. Okay, so earlier we have seen the traditional GANs and DC GANs. Today we will be talking about paid image-to-image translation, specifically Pix2Pix. So let's see what we have. So in this lecture, we will be talking about conditional GAN architecture, paired image-to-image translation, and then like how you can train Pix2Pix, and then we'll see small code where you can code your own pixel to pixel GAN. Okay, so conditional GANs, let's just first start with some brief introduction. So this is a type of GAN where both generator and discriminator are conditioned on some additional information. Okay, as the name specifies conditional GANs. So we are actually giving some condition as the input, and the output is actually generated based on that condition. Okay, so let's just see. So that means generating specific output based on the given condition, providing more control over the generation process compared to the standard GANs. Okay, so this conditional information could be a class label, could be a category, for example, type of animal, object, or even another image or type of description. So for example, let's say if I give some random noise as the input, and if I also give this thing like, okay, please generate a dog image. Okay, and then the output will be a dog's image. Okay, so that kind of conditional information actually helps to control the kind of output that you are generating from the GANs. Okay, so the architecture, let's say if we see, so there are uh, the architecture stays the same. There is a generator, there is a discriminator, but the underlying neural network for both the generator and discriminator differs heavily from the traditional GANs. So in the generator, we had only the random noise as the input in the traditional GAN, but here we also have a condition vector. So for example, a class label as the input, and it uses this combination of the inputs to produce an output that matches the specified condition. Okay, so for example, let's say if I say that, okay, please generate a dog's image, and this is a random noise, then the output will be a dog's image. Okay, and the discriminator is that it takes both the generated or the real image and the condition vector as the input, and learns to determine if the image is both real and matches the condition. So for example, here, let's say the discriminator's goal is not to only say that the generated image is real or not, but it also says that, okay, yes, let's say here I took an example of dog. So it will also say that, okay, so the image is real and it indeed matches the dog. Okay, so that is, and the discriminator's output is also not only real and fake. The objective function is similar to the regular GAN, but it incorporates the conditional information C. We'll see how it is done. The interpretation is that the discriminator must verify that the data is both real and conditioned correctly on the vector C. This is only C, while the generator tries to produce realistic outputs that also matches the condition. Okay, so let's see how these things are actually used in practice. So one of the common application is image to image translation, where we transform the images based on the specific condition, such as there is a commonly used model pixel to pixel, which we will be talking in this lecture as well. So it converts an image to a target domain. So for example, you can turn a sketch into a photorealistic image. You can turn summers into winters. You can turn horses into zebras. Like, so there are so many examples. Cycle GAN is another extension of the conditional GANs, which translates the images between two unpaired domains. Okay, so for example, turning a summer landscape to winters. So basically, I think I gave this example in this as well. Because we know the domains here. If there is a corresponding match, this particular problem can be pixel to pixel or the paired image to image translation as well. But let's say when we don't have the pairs between the summers and winters, then it is actually a unpaired image to image translation. Okay. Another important application is super resolution, where we actually transform images from lower resolution to the higher resolution. And this is a very important application in, let's say, media industry. Text to image generation. So, for example, generate images based on the text description by conditioning on the text embeddings. Nowadays, you use LLMs, but the field of LLMs was actually very late, but the GANs were proposed in 2014, 2015, and people were actually using GAN-based models in Gen AI first, and then transformers came into existence, and then whole LLMs came into picture, and then you use Gemini, ChatGPT these days. Now, attribute-based generation. So, for example, you can specify facial attributes or the facial features or object characteristics. So, for example, let's say I want to generate a face with a smile, okay, or with a black hair, or maybe some object shape you want to do, right? So, based on these attributes, we can actually generate the images. Okay, so this condition is given as the input to the generator and also to the discriminator. Okay, so let's just see how these things are actually done. So this was like a brief intro about it. Now let's just go deeply into one of the model, pixel to pixel, which actually do paired image to image translation. Okay, so in this lecture we will be only talking about paired image to image translation, but there are other things as well. For example, unpaired image to image translation, unseen image translation, which we will be seeing in the coming lectures. Okay, so let's just first see what is paired image to image translation. So for example, let's say if there is a colored version of an image, and if I want to convert into the grayscale image, it's actually very easy, right? It's an easy problem because you have to remove some information by retaining the shape. Similarly, let's say if I talk about downsampling, it's actually very easy. You have to remove some information and you can actually get the lower resolution version. But let's say on the other hand, if I say that, okay, so there is a grayscale image, if I want to transform it to a colored image, it's actually a very difficult problem because, right, you need to understand like, so which object needs to be filled with which color. Okay, similarly, if you want to do super resolution, it's a very difficult information because you have to add the information which is especially coherent with the existing pixels of the image, and the resultant high resolution image should make sense and it should be relevant to the input given. Okay, so this is a very difficult problem. So let's see how GANs can actually help in solving these difficult problems. Okay, so another example, let's say if I give, let's say you have an RGB image, and if you want to create the segmented mask of it, it's very easy, right? You just have to identify, okay, so which are the like objects here, and you can turn those pixels into one particular object. Okay, but let's say if I say the other way around, it's actually a very difficult problem. Similarly, from depth estimation, from an RGB image to depth, maybe very easy, but from the depth to the original image is actually very difficult. Okay, so what is paired image to image translation? Let's say we have two domains of images. Let's say one domain of images is, let's say, the sketches or the edges of objects. Another image, another domain is the corresponding, like the photorealistic image. Okay, so we know what is the correspondence between each image in the two domains. Okay, so that means we know that these particular edges corresponds to this particular shoe or maybe some other shoes as well. Okay, this particular edges correspond to this particular shoe and so on, right? So we have some correspondence between the two domains. So that means there is a pair between the two domains. So what we want to do is we want to transform this particular images from one domain to the another domain, okay, where we know the correspondence. Okay, so let's just see an example. So from the pixel to pixel, image to image translation paper, which was proposed in CVPR 2017. Okay, if you are interested, you can go to this particular paper and go into the more details of it. Okay. Okay, so let's say we have an image X as the input. Okay, so we are actually giving instead of the random noise, we are giving a input condition. Okay, so we have given an image as the input, and then there is a generator G, which actually generates a realistic image of the input condition that is given, and the discriminator says whether it's real or fake. This is still a GAN network. So a generator actually generates a fake sample that can fool D, and D classifies whether it's a fake or the real sample. Okay. So this is what the problem in the standard GAN. Okay. So now let's just see about one particular example. Let's say we have given this particular condition as the input, and the discriminator has says that it's a real image. But let's just consider another uh, problem where this is a condition we have given, okay, that there is a bag, and it actually generates an image of a bag. Okay, discriminator says that okay, the input image looks real too, right? But here we don't want this. Here we don't want that. Okay, so this is a GAN model, but we don't want this particular thing to happen here. Okay, so in the standard GAN, the min-max optimization is actually used, and this is the notation for it. Okay, and it's actually you can say that you can say that this is an adversarial loss. We have discussed this in the first or second lecture. So if you want to see how this is actually formulated, you can go to that lecture and see how this is done. But this is for a conventional GAN. And you can see that, okay, so this is the real, this is also real. That is correct. But we don't want this particular output. So what is it that we need to change in this particular architecture? Okay, let's just see. Okay, so here, let's say we have given this particular sketch as input to the G. Now, this is the GX, and the discriminator actually wants to say whether it's a real or fake pair. Okay, earlier we were saying whether it's a real or fake image, only the input. Okay, but we were not considering this as the input to the discriminator. Okay, so here we are considering both as the input to the discriminator. Okay, and we will say that whether both the inputs are the real pair or the fake pair. Okay, so to incorporate that, the min-max loss function actually is modified in this way. Let's say the output, let's say when we give the sketch X as the input to the generator, the output will be G of X. Okay, so for this G of X, whether the X is actually a right image or not. Let's say the corresponding ground truth image for this is, let's say, Y. Okay, and let's say when we give this particular thing, okay, it's actually a real pair, and discriminator actually say that okay, it's a real pair or not, and so this is how the min-max loss function is actually modified when we consider this conditional input, additional conditional information as the input of the discriminator. Okay, generator stays same. The random noise is actually replaced by this conditional information, but the discriminator actually takes two inputs. Okay, so the min-max loss function is actually modified in this particular way. This is actually very simple. If you guys have any query, please comment. We will I will try to answer the corresponding questions. Okay. Okay, I think this is actually you have understood. It will say that, okay, whether it's a real pair or fake pair. Let's say, what's the probability of it's a fake pair? Very, very small. Okay, 0.1. It looks a real pair. Okay, so now what is the probability that it's a real pair? The probability is very high. It's 0.9. Okay, so this is the corresponding one. Okay, so this is how our loss function is actually used here. Okay, that I have explained in the previous slide. Similarly here as well. So let's say This is about the fake pair. When the input is given from the generator, this particular probability is coming into picture. And when you are giving the real pair, Y, then this particular probability is actually coming into picture. Okay, so this is very simple to understand. Okay. So now, so if we talk about the training of pixel to pixel GAN, then instead of the conditional GAN, like whatever we have discussed in the modifications of the objective function, there is also L1 loss added to the objective function. So, for example, the min max loss that we have, like that we have seen in the previous slide, one L1 criteria is also added. Generally we use this for regularization purpose. You can assume that this is also used for the regularization purpose, so that we can stabilize the GAN training and the weights doesn't vary too much between the iterations. Okay. So when we have actually added this L1 loss function into the loss function, the researchers actually noted that it achieves faster convergence and the stable training. Okay, so the pixel to pixel GAN actually uses this particular loss function along with the min max loss. They are also using this L1 loss criteria. Okay, that is added with a hyperparameter lambda. Okay, so this is how the things are actually going. Okay, so this is the generated output from the GAN, and this is the real output, and this is how you actually modify the uh, loss function of the GAN. Okay, so now let's just talk about the architecture of the pixel to pixel GAN. Okay, so now how is it that you can actually take image as the input and generate image as the output? Okay, how to do it? Okay, so till now we have only seen that. Okay, so in the DC GAN we were actually upscaling, and it was like from the random noise it was generating an image by upscaling. But here it's an image. We have to generate the same dimension image. So what is it that we can do? So there is a model called patch GAN. Uh, Okay, so and you must be knowing about the encoder decoder architecture. You can also see UNet architecture, so which actually uses skip connections in the encoder decoder architecture. Okay, so if you don't know what is UNet, I think you can go to this particular paper and see the details. And if you guys have any specific query, you can comment as well. This is not very difficult to understand, so I will only say assume that you guys know it. So this is very very simple, and like it's like a REST net. Okay, so where there are skip connections, and but the model is encoder decoder based. Okay, skip connections are there, decoder condition on the encoder activations. Okay, this is the only thing we have. Okay, so you know that there is an input image, it goes to a latent representation, and from the latent representation you actually try to reproduce the same image. Okay, so that is what here the thing is. But here it actually transforms from one domain to the another domain. Let's say the domain one we have of the image, and then we will transform it to the second domain. It's not the in the encoder decoder we usually try to produce the same input image, so that we know that this latent representation is actually like very small representation of the image, like kind of features. But here we actually try to like generate an image of the second domain. Okay, so this is how the pair-to-pair image translation is actually working. And the discriminator is actually nothing but a patch gain, which takes two inputs, the two images as the input, and it will say whether they are same or not, whether they correspond to the same particular pair or not. Okay, so if we see about the output of the pixel to pixel GAN, so let's say when you give the aerial images as the input, it will generate the satellite imagery. Okay, just see right how realistic the output is coming out. Okay, similarly you give this segmentation mask of the floors, so then it will generate the like very real looking like images. So this is the ground truth, and this is the output of the pixel to pixel GAN. So actually this information is actually a little confusing, but things are actually very clear here. Okay, similarly here if you see, this is the building, corresponding building of this particular mask, and so this is the image generated by the GAN. Okay, see how high quality the images are generated by the pixel to pixel GAN. Okay, if I give you another example, so these sketches are transformed into these outputs. Just see, right? It is actually, I think this one, if you see, like this is more good than the ground truth, and similarly, this is also very good. So things are actually coming out to be very good as in the output. Similarly, like when you transform day into the night, so then this is the output image you are getting. Okay, so I think the output that I'm seeing from the GAN is actually looks more good to me as compared to the ground truth, because this still looks like a day to me, but this clearly looks uh, like a night. But see, the here it looks like that there is a water, but here actually this is a road, right? So some things are actually problematic, but I think the scenery is actually transformed very well. Okay, so like I think let's just see how L1 loss is actually coming up well in this. This was actually explained in the unit architecture. Okay, so where when we incorporate this L1 loss, then the things actually look more better. Like only if you use only L1 loss in the encoder decoder, this is how the things are, and in the unit, how this is how the things are. But let's say we when we do GAN plus L1 loss, the things are actually a little more better. Here you can see that okay, there are different objects are there, okay, but these are not clear. But in the unit, this is a traditional encoder decoder, but in the unit you can say that okay, yeah, there these are cars. Okay, so this is how the different components of the loss function are actually helping. Okay, so this is just have actually shown this in their paper. Okay, so I think we also talked about how is it that you will evaluate the GANs. So here also I think there are two matrices used, and the realism. Okay, so based on AMT fooling rate and diversity, how diverse the outputs are. So this is actually described by LPIPS feature score. I think the higher the better it is. Okay, so if you see right, so this is pixel to pixel GAN. Uh, and this is bicycle gain and this is the CAE gain. Okay, I think well, this is I think lower the better it is. I'm also not sure like how this is actually read, but this is how the performance of the different gains are actually compared. Bicycle gain and the CAE gain like are also conditional gain examples. Okay, this is pixel to pixel. Okay, so this is what we are actually seeing in this particular lecture. Okay. Okay, so this is the actual pixel to pixel architecture. So where the generator actually is nothing but an encoder decoder architecture, where this is the encoder which actually transforms the input condition image into a lower dimension information, and then the decoder of the generator actually transforms this lower dimension into the second domain of the input image. And then there are residual blocks which actually provides a skip connections from the encoder to the decoder. Okay, so that the information from the one domain can be transformed in this into the second domain. Okay, this actually helps a lot in the RESTnet as well. So the same architecture is actually incorporated in the UNet. Okay, so this is taken from the UNet. Okay, so this is how the things are actually coming up, and this is the input labels, this is synthesized image, and this is the interactive editing result. Okay, so I think this is something interactive results which was proposed in the the conditional GAN paper from 2017. I'm not sure if this is the same paper as the pixel to pixel GAN. Okay, so now I will be talking about the coding part of it. Okay, so I will only go into the little details. I think this is where we are actually. Okay, so if you guys need this code, you have to comment and ask me for it, and I will give you that. Okay, so this is how this is actually the data set of the face images. Uh, Okay, no, not the face images. I think facades are basically the floor, multi-floor buildings are actually there. So I think I will not go into this. This is just the image operations. And so I will just say, okay, so this is the one domain of the images where we have segmentation mask of the floors, the multi-floor buildings, and this is the second domain where we have the corresponding multi-floor buildings of those segmentation masks. Okay, so this is how we have coded that discriminator. Discriminator is nothing, but it takes two inputs as two images as the input, image and the target. Okay, so we take two images and we concatenate them, and this is actually given as the input to the conv layers, and then leaky ReLU and batch normalization and so on. Like we repeat it several times, and then the output is whether this is a real pair or the fake pair. Okay, only one particular output is actually given as the output of the discriminator. Okay, so this is the description of it, and basically this is not one output, but this is actually uh, mm, yeah, actually a sigmoid output is actually given here. Yeah. Okay, so okay, so a convolution layer only with the one particular kernel is actually used here, and the output of the image is actually considered based on the like how the input image is actually provided. Okay, and this is the encoder, and this is a decoder where the encoder actually takes an input image, and then it actually applies the convolution filters to transform it into the lower dimension representation. Whereas decoder is actually using transposed convolution, and it actually transforms it into a bigger size image. Okay, and generator is nothing but it's a sequence of encoder and decoder layers. Okay, first the encoders are there and then decoders are there. Okay, this is what it is happening, and maybe you can train it, and all the things are actually written here. And I think okay, here I have stopped the training, and you can see I think things were working well. If you want, I can give this code if you ask so, and we'll like we can discuss if there are anything that we need to discuss. Okay, thank you. Okay, thank you for attending this lecture. Now see you in the sixth lecture on unpaired image to image translation, and we will be talking about cycle GAN in that. Okay, so and if you are interested in our AI club, you can join our WhatsApp channel using this link. Okay, thank you.